Thank you all for coming today. Really appreciate you coming out. I'm Matt Chandler, Director of Global Public Relations at QNX. Yes, Director of Global Public Relations probably seems like a kind of funny title for someone to be delivering a talk to the Computer Science Club around, embedded engineering, embedded software. I'm the pinch hitter. So originally there was going to be another person delivering this talk, but we're having we had an engineering fest at our headquarters in Canada earlier this week. So he's there with the team, and they called me in kind of last minute to provide an overview for you all in terms of a bit of the corporate history of QNX, how we came to be where we are today, and the various industries we play. So before I get into the first part of the talk, I'd love to get a show of hands. How many people were familiar with QNX before this year? Show of hands. Okay, so maybe 30%, 50%, not a ton or whatever. What about BlackBerry? How many people were aware that BlackBerry had transitioned from mobile phones to software that's now in vehicles? Okay, a few more. Okay, great. Well, hopefully after this presentation, and my colleague Elad is going to be delivering a more technical talk, you'll have a lot better sense of our history and why it can be so valuable to learn about QNX foundational software. So I mentioned that QNX is part of BlackBerry. BlackBerry is a bit of a Frankenstein of parts, I should say, from various acquisitions, that the company acquired over the years. So there's two business units. There's QNX, which we're going to be spending the bulk of our time talking about today, and then there's the secure communications side of the business, which is historically sort of cybersecurity related. It's a three-legged stool of products. You can see there the first being BlackBerry UEM, Unified Endpoint Management. So this is software that big organizations would use to determine what policies and applications you can use on your work device. Then there's BlackBerry Ad Hoc, which is our critical event management platform, again geared towards large organizations, government. It's sort of push notifications in the event of an emergency. So let's say there was a tornado heading to this building right now. If the University of Waterloo had Ad Hoc on all of their employees' phones, they could send a notification immediately to everyone to say, hey, this is happening, this is where you should go to be safe, let us know your whereabouts. And everyone would be able to acknowledge, so they can immediately sort of account for their people. Or it could be a cybersecurity attack, any sort of instance where things could go wrong on a mass scale. This is kind of like the Amber Alert type system that's used by big organizations, manufacturing facilities, governments, and whatnot. So that's Ad Hoc, and then there's BlackBerry SecuSUITE, which is secure enterprise-grade communication technology. So you think about the leak that happened earlier this week with the Trump government and the national security team, the defense secretary, using Signal, a consumer-grade application, unexpectedly inviting a journalist into the conversation. Which, how do you do that? Those sorts of applications are not meant for national security, but SecuSUITE is. SecuSUITE is used by NATO for extremely sensitive communication. This is the kind of stuff that governments should be using. So I'm sure a lot of our sales folks are knocking on a lot of doors to be like, hey, this is what you need, So that's the secure comms side of the house. Then we've got QNX, and under QNX there's QNX Software Solutions, which I'm going to be going into in a lot more depth. Then there's BlackBerry Certicom, which is end-to-end cryptology, primarily for vehicle-to-vehicle communication or vehicle-to-infrastructure. So you think about, as vehicles become more and more autonomous, all of those vehicles need to be able to talk to one another, right? Talk to one another to make sure that there's no issues, and you can't have any sort of disruption within that communication. And that communication could also include communicating to infrastructure. So you think about streetlights and stop signs and all the different things that ultimately our smart cities will have. Certicom will enable that communication to happen seamlessly. Then there's QNX Ivy, which is our car-to-cloud big data management platform. You can think of this as something that enables you to pull data off of various sensors within a vehicle, and then use that sensor data to deliver insights that can be turned into new features and capabilities. So for instance, I'm a dad, I've got 2 kids. Let's say my car had Ivy within it. and my kids jumped into the back seat, IVY would immediately recognize that there are children in the back seat based on the weight. Based on that weight, it could determine, okay, I'm going to send Matt a notification if they haven't got their seatbelts fully engaged. And also, because I know that they're kids, I'm going to make sure that the infotainment screens in front of them only play approved content or music without explicit lyrics. So it's a new way to pull different sensor data off a vehicle with a view to delivering different types of features and capabilities and functionality. Lastly, there's BlackBerry Radar, which is it's the only hardware part that still exists of BlackBerry's legacy business, and it's asset tracking. So it's sort of a box half the size of a laptop that you would mount on the exterior and interior of a big rig truck. And what that device does is it transmits sensor data back to a fleet owner about the vehicle's whereabouts, how full the load is. So let's say you're Amazon and you're taking a bunch of packages to the other part of the country and only half of your vehicle is full. Radar would enable you would give you that notification so that you could maybe pick up some additional loads along the way. So it's great from an efficiency standpoint, right? Maximizing the ROI of your assets. It also provides you data on a number of different sensors. So it could be, excuse me, it could be the temperature within the vehicle. It could be the humidity levels. It could be the location. Maybe it's gone outside of a geofence that it should be, and all of a sudden you realize, oh crap, my vehicle might have been stolen. You think about if you're transporting something like tomatoes that need to be transported in a certain type of temperature, have a certain type of humidity, Radar would be able to tell you if that threshold had been exceeded. And there's lots of different other applications and use cases if you think about, the right temperature that wine ought to be transported or pharmaceuticals or whatnot. So there's a lot of value to this platform. I'll just pause there. Actually, if anyone has any questions throughout, I'm certainly open to taking questions, but I know we're going to have some time after this as well. But feel free to throw up your hand if you have a question that's burning. So again, we're here today to talk about QNX. That's the rest of the portfolio. Really what you guys want to know about is QNX. And what QNX provides is a trusted foundation for software-defined businesses to thrive. So we lead the way in delivering safe and secure operating systems, hypervisors, middleware solutions, development tools, along with support and services delivered by trusted embedded software experts. So QNX is deployed in the world's most mission-critical embedded systems and applications around the world, including more than 255 million cars on the road today. So if you drive a vehicle, if your parents drive a vehicle, if your friend has a vehicle, there's probably a good chance that QNX is powering some aspect of the software stack. We've been around for 45 years. And in fact, one of the computer science, one of the students here was giving us a tour of the lab where the germ of the idea for QNX was actually created in the Trains lab upstairs, which was pretty cool. I'd never heard that before. I guess this was in the late 70s. So we were founded in 1980. In fact, we were founded on March 30th, 1980. So on Sunday, we're celebrating our 45th birthday. Don't ask me how we're marking it. Hopefully no one's working. It's a Sunday. I don't think there'll be any cake. We'll see. We were acquired by Harman in 2006. And then we were acquired from Harman by BlackBerry in 2010. And BlackBerry acquired us in order to create the BB10 operating system. So this was the operating system that went in a lot of our old phones. It went in the playbook, if any of you guys know that reference, sort of a poor man's iPad, if you will, that did not pan out. But we've obviously come a long way since then. We translated that operating system heritage to mission-critical applications. We've got 850 employees globally around the world, and our headquarters is in Canada, which is just outside of Ottawa. You can see there we've got a number of locations around the world. We've got 600 different product SKUs within the market, and 500 of those 850 employees are engineers, software engineers, developers. We've also met 300 plus starts of production programs, so making sure that our software is ready when an automaker is ready to put that vehicle on the line. And you can see the various industry certifications that our products have. And these are very critical certifications. So for instance, if you want to release a new medical device to the market, you need to have IEC 62304 Class C, which essentially means if this software fails, someone could die, or someone can be badly injured. So all of this software needs to be certified to make sure that that is not a possibility whatsoever. And that's what our software enables companies to do, is make sure that the products they release to the market are completely certified, whether it's a next generation connected car or the knife that a surgeon might use in an operating theater. So again, we've been around since 1980, but just this past January, we relaunched the QNX brand. Because we've been acquired by various companies over the years, we kind of felt like we were always in the shadow of BlackBerry, right? BlackBerry was the consumer brand. Everyone knew BlackBerry, everyone knew the phones. QNX was kind of a bit of the forgotten stepchild. But despite that, our customers still knew us as QNX. So if you were talking to someone in the automotive industry, they would always refer to us as QNX. So just this past January, we took the step sort of to provide ourselves with a little bit more autonomy, stepping out from BlackBerry's shadow, and to lean into that brand equity and heritage that exists to the QNX brand. So I'm just going to play a quick video that I think does a good job sort of telling a little bit of that heritage story. And hopefully the sound works here. I'm going to turn off my mic so it's not.
Okay. Hi, I'm Eric from QNX. In this video, I'm going to talk about what you need to do to get your free non-commercial developer.
That's coming later, so we'll hold fire on that for now. Okay, so hopefully that video paints a bit more of a compelling picture of the company as opposed to me just talking about it, right? You really get a sense in terms of we're on the cutting edge of so many fascinating industries, all of which are becoming more and more software defined, right? And a lot of that focus was automotive, which is our bread and butter. It's where the bulk of our revenue comes from. It's what most people are aware of QNX from. But like I said, there's medical devices, next generation medical devices. Industrial robotics is a huge and burgeoning area for us. If you think about Amazon warehouses or these massive warehouses, there's fewer and fewer people operating them, but they've got lots of these robots running around transporting packages and whatnot. So a lot of our software powers that kind of stuff as well. And then obviously lots of the different big, vehicles that you might see in a mine or on a massive farm or whatnot, the kind of stuff that again needs to operate 24/7, 365 days a year, reliably, securely, safely, without fail, right? So this is nuclear power plants, this is oil and gas refineries, this is, fighter jets, right? There can't be any room for error, and that's what our software provides. A few more stats in terms of our presence within the automotive market. 270 makes and models 10 of the 10 top biggest automakers in the world use QNX software. 24 of the top 25 EV manufacturers. You can take a guess which EV manufacturer does not use us. The CEO is heavily involved with the government right now. We won't spend too much time talking about him. Maybe he'll come around eventually. 45 plus automakers, and this is not just, with respect to one particular market. We kind of think of ourselves like Switzerland. We'll play with anyone: Chinese, Japanese, Korean, American, German, startups from Silicon Valley, the old school legacy Detroit automakers. All of them are transitioning to software-defined vehicles. Whereas in the past, a lot of the value of a vehicle was in shaping steel and bending metal. Nowadays, it's much more focused on software. Software is driving the evolution of the automotive industry. When you look at the schematic, the amount of different domains and areas that software is powering, it's like night and day versus 10 or 20 years ago. You can see there a number of these areas we've been in for over 10 years, and a handful are more recent for us. But software is now powering everything from advanced driver assistance systems. So you think about when you go to switch lanes, you get a little notification if you're driving a more advanced car. Your infotainment screens, right, in front of the dash. Battery management, if you drive an electric vehicle, an estimation around how much range you have so that you don't get stranded on the side of the highway. Body control, smart sensors, backup cameras, brakes, it's all powered by software. And whereas previously a lot of these modules were controlled by distinct ECUs, so let's say you wanted to roll down your window, you would press a button, that was an individual ECU. You wanted to back up, that was an individual ECU that showed your backup camera. Now what's happened is all of those ECUs are consolidating on a handful of domain controllers. So they're having to do a lot more, and majority of them are having to do safety critical functions and non-safety critical functions. And that's where our embedded software really comes into play, because we're able to partition the safety critical use cases apart from the non-safety critical use cases, so that if your infotainment system goes down and you lose access to that all of a sudden, it has no bearing and no effect on the stuff that is really critical to making sure that you get home safe. So here's an example, probably AI generated, of a futuristic next generation vehicle. You can see, again, one clear dash, a lot's happening. You've got infotainment, you've got ADAS features, you've got navigation, you've got a digital instrument cluster, a whole lot's happening. And so what we do is we enable, we enable our customers to deliver custom occupant-centric experiences on demand, safely, securely, economically, and at scale. And again, I want to play another video here for you guys that
Let's take a trip to the beach.
Speaks to the IV product that gives you a bit of a sense in terms of what could this vehicle of the future look like, and how is it software defined. Just going to mute my mic.
In the future with BlackBerry IVY. Let's take a trip to the beach in the future with BlackBerry IVY, a new automotive software technology.
The joys of technology. Sorry about that. How are we doing? Good?
Let's take a trip to the beach in the future with BlackBerry IVY, a new automotive software technology poised to transform and customize everyone's driving experience. Imagine driving a car that conforms to you, dynamically adjusting its settings for each driver, including how much battery charge is left, by estimating vehicle range with a partner battery software application. IVY shares sensor data and makes smart predictions and recommendations in real time to make driving safer, smoother, and yep, more fun for everyone on the ride. Even the kids, by activating child locks and ensuring the entertainment is kid-friendly. IVY transforms your car into a secure wallet on wheels, making payments for tolls, parking, and charging stations effortless. With BlackBerry Ivy, trips to the beach or anywhere will never be the same again.
So here you can see, basically it's all of the familiar brands you guys know, right? BMW, Audi, Ford, General Motors, a lot of new EV upstarts, Chinese. Again, you can really see the presence that we have within automotive. But it's not just limited to automotive. QNX products are in millions of critical IoT systems and infrastructure, everything from slot machines to safety critical controllers to movie production cameras. We talked about asset tracking, flight simulations, x-rays, mammography machines, from soup to nuts essentially, right? And so what are the trends that are driving more powerful embedded system software, right? Like, why do we keep seeing so much business? What are the main trends? Well, like I said, a lot of these industries are becoming more and more software defined, right? We talked about the mixed criticality aspect of next generation connected cars, right? And being able to partition safety specific use cases against non-safety specific use cases and whatnot. That's happening across multiple different industries, and that's, again, a real sweet spot for QNX with our hypervisor to be able to do that. More CPU needs and intelligence blending between cloud and edge, being able to process data up in the cloud and on the edge at the vehicle, and being able to toggle and distribute that load at the same time. Increased safety and security requirements and regulation. When we think about something like healthcare, and this obviously is not necessarily just specific to North America, but fewer doctors out there, growing populations, more technology being called on to do teleoperation or remote procedures. Bringing more and more robotics into the operating theater, that all comes with risks, right? And so as a result, there's a ton of new regulations that are coming onto the landscape that require those certifications, for which, again, we have that enabling software that allows our customers to make sure that the devices they put out to market are 100% safe and secure. High performance computing due to higher functionality expectations. Again, that sort of ties back to everything becoming more and more software defined. These are not dumb sensors anymore. They're very sophisticated, very complex, which is where we like to play, is in sophistication and complexity. And then lastly, next generation SoCs from top vendors, right? The likes of NVIDIA and Intel don't rest on their laurels. New capabilities, that works to our favor as well. So what is QNX? And again, I'm going to go over this very briefly because my esteemed colleague Elad is going to go into it in a much more depth. But the QNX operating system is a real-time microkernel-based POSIX operating system. You're able to isolate system functions for very high reliability. It has real-time scheduling for CPU and resources, and it's compatible. It has compatibility with probably a lot of the familiar frameworks and tools and libraries that you guys are familiar with. The way it's built, its architecture is that it incorporates security and safety by design principles, and it comes with pre-certified components for streamlined certification efforts, which again is a big reason why our customers seek out our products. So why learn QNX? What's in it for me? Why am I here tonight? Considering learning a little bit more about QNX. The reality is, you learn QNX, you come with a skill set that is in very high demand these days, right? We looked at all those different industries that are becoming more and more software defined. They're looking for graduates who have these sorts of skills, whether they're embedded system developers or cloud developers. They're looking for people who know about RTOSes and hypervisors. They're looking for people who know about device drivers. QNX is the software that's powering the future. And so if you are able to familiarize yourself with it, try it out, learn it, get better, it's something that you can put on a resume that would look really good with a lot of these big companies out there who are using it. Whether you're interested in, one day working for a big automaker or, a big manufacturer, all of them have this need. There's this huge, dearth of top embedded software talent. And this is the kind of thing that can set you above the rest. which is a big part of the QNX Everywhere program and part of the reason why we're here today speaking to U of W, you guys, right? QNX Everywhere is a new initiative to address the growing global demand for highly skilled embedded systems developers. There's not enough out there, and there's not enough QNX developers out there. If you Google or go on LinkedIn, you know, QNX developer, or you look on some of those big companies, a lot of them will list that as a skill set, you know? So there's a ton of value to getting in on the ground floor as opposed to, you know, entering into the workforce and only learning once you're at a company. So our goal with QNX Everywhere is to increase the awareness and branding of QNX. You know, it's about expanding the number of QNX-trained developers globally and developing that broad and active ecosystem across key verticals like we spoke about, industrial, medical, automotive. You know, we're trying to spread the word, engage with more post-secondary institutions globally. We put out an announcement a couple of weeks ago with a partner in India that is looking to essentially do this kind of stuff with 100 different schools across the Indian subcontinent. India being obviously a ground zero for talented software developers. And at the end of the day, you know, we want to create an active QNX global developer community. So we finally opened it up. Previously, you could only access or learn about QNX if you worked at one of these big companies, one of these big automakers. That's no more. You can now get a free license if you're wanting to do something in a non-commercial fashion. And again, we want to empower developers to build QNX-based software-defined products for both automotive and the general embedded market. And part of that is broadening access to, you know, the QNX ecosystem, tools, solutions, integration, training. We just last week or the week before made our entire library of online training available. Again, previously you had to pay for this. It was in person in Canada. Now it's all available for free. So I think it's something like 40 hours. Lots of different courses that and specifics that you can look into. You can see there learning.qnix.com. And at this QR code or that URL, you can get a free license, get everything you need to get started so that you can start playing around with it, so you can start familiarizing yourself with our operating system and our software. And then we also have that QR code for our developer blog, which is led and overseen by my colleague John Hamm here. He keeps it filled with lots of new content, tips and tricks, that kind of thing. Last but not least, I'd be remiss if I didn't mention to you all about as part of that brand relaunch, we also launched a new podcast called Code of the Future, which is all about offering insights into the innovative world of embedded software in different industries, from automotive to medical and whatnot, speaking to experts both at QNX but also from across the industry about where they see the future headed. Technologies, trends, whatnot. We've had some fascinating people on the podcast. Dolby Atmos talking about sound within the vehicle, the sound revolution within the vehicle. SPD Automotive CEO talking about the rise of the Chinese OEMs and what that means for the North American and German automakers and whatnot. And actually, just earlier today, we put out a new episode with Motor Trend's head of editorial, Ed Lowe. Quite timely, obviously, with the tariff news that Trump made yesterday. But it's a great resource to check out if you want to keep tabs on what QNX is up to and sort of our perspective of the industry and where it's headed. So definitely give it a listen and give it a follow. And again, hopefully this provides you with a little bit more of a background in terms of where we are, the industries we play today, and where we're headed. And I think we're going to take a little break, and then my colleague Elad is going to dive into some of the more nitty-gritty specifics of the microkernel. So I'm happy to take any questions if anyone open book. Yeah, go for it.
One question I have was, you talked about there being a hypervisor.
Yeah.
So how does an operating system that is basically you are RTOS, right?
Yeah.
So where does a hypervisor come in for RTOS?
I'm going to leave that one for Elad.
It's an excellent question. I will answer it.
Yeah, I think a lot of the technical content will be covered in Elad's presentation. Yeah, go for it.
Sorry, another question.
Oh. Anyway, yeah, go for it.
Yeah, I mean, from a business perspective, here you have a lot of business in Canada.
Yeah.
A what are your like plans, or if you have any thoughts around like the incredible part theft problem we have?
The incredible what, sorry?
Part theft problem that we have. Are you like working on anything new
Yeah.
or related to that you can share?
Not that I'm aware of. I mean, it's definitely a big issue. I think it's more an issue that is solved by the OEMs themselves as opposed to, you know, us, because we're very, you know, low down in the software stack. Yeah, so as far as I mean, I know the OEMs recognize that it's a big issue, but ultimately it's kind of on them to figure out. So our software doesn't necessarily have any bearing on, you know, how easy it is to steal or hotwire a car. You know? Yeah. Any other questions? No? Okay, cool. Well, it looks like food is here. So, yeah, if you're hungry, dig in. Thank you.
The ease of it's not the only thing.
It's not impossible, but
Like, what is even the use case?
To the car manufacturers, they want to use as few resources in the car. They want to put distribution tasks to make it. But for the entertainment, they'd rather use. They used to use No. If you do it, this is what I said actually. In that scenario, I don't know if I use the same terms you're not familiar with. So the QNX system in the hypervisor is actually a process in our host operating system. So the guess is only answered.
So you basically behave like an hypervisor such that they can have other software running.
And that's completely legit.
Yeah, that makes sense. That makes sense.
That's no worse than running any application in a mixed reality.
And it gives them like a sandbox environment where they can run their own stuff.
Yes.
And you can keep running your own stuff.
Correct. So that's legit. There are cases where people want to put a QNX system on top of the hypervisor that
Yeah, then it's like some mess up, but then you have like performance.
it's that's not the main concern. There's actually no performance issues on this one. The main concern is that the hypervisor can decide, because it's more powerful, to take away the system. For how long? We don't know.
Like, if it's your hypervisor, like that,
Still,
can be like a
so the legitimate, as I see it, this is just my opinion. The legitimate case is the host is QNX, the host that's running your critical stuff. You have a VM that's like running a VM your right?
It really makes it much better. And I can use AI to
And like, what is the? You presented that as this as your opinion, so that means car makers don't need to make this.
Some do, some don't. We have very little control over our system once it goes in the wild.
Because at that point, I assume you own like SaaS.
Yeah, we don't build complete systems. So we give you all the tools to either hang yourself or come up with a great system.
So so like in that sense, we're like at protocols, and then like every like the end product shipper modifies it such that like they can.
And often they will only come and talk to us at the end of the project when we realize that something doesn't work instead of at the beginning of the project. How do we design the system?
The thing is that at the beginning they would have to pay you.
That's people.
Apparently after she left. Sorry. No,
Oh, really? Okay. And you moved here recently, or? Oh, wow. Okay. Well, Harrison, nice to meet you.
honestly, man, probably more Alex.
Wow. Do you remember anything from it? Like when you were there? Is it, oh, okay, yeah, sorry. If they moved 3 years ago. Yeah, you don't look 50. Behind that. Oh, okay. Yeah, sorry. Oh, no, I know that.
What's that thing?
He's mentioned his speed, so he started.
Oh.
I'm taking that exactly.
Sure. So the people who founded QNX in 1980
Oh, you saw me or something? Oh, no way.
some of the information I'm going to present.
Yeah, it was easier than I don't think it'll be hard. Also, like, everything's been getting curved so, like, crazy. Like, I got 17 out of 20 on the second midterm, but they still gave me a 95. Yeah.
No, thanks, I'm good.
Yeah, it's a good question. It's a good question because I also might have requirements for all companies unless I don't. We'll have yeah, that's what I thought would happen, but she told me if you drop out, like it makes sense because you still took the 3 courses in that area, so you still have the knowledge of some of that. It makes sense that we're not doing yeah.
You guys setting up?
Oh,
Oh, there you
yeah, they're because they're lectures are most have lectures, but they always place them on regular days, but they don't have regular lectures. flexible. Then they'll have makeup levels once they're gonna use. Then they have tutorials. I don't know. It's like when a lot of engineering cops they work on their talks, and so they go over the talk. But like they will show up with us, and then they'll also do like I don't know.
This is the last event.
They have tutorials, and then they have a lab, and then somehow have to figure out how to squeeze in 4 more courses that go through the lab. So if they probably don't, yeah, they don't like to. They don't want to.
One thing that was working.
No, they don't like it. Yeah, unless you have one of the props, eat like frog. It's like crazy.
Like, yeah.
That's crazy. Everyone was shocked. Actually, a lot, pretty much just all, not all, but like a lot of the theoretical ECUs. A lot of the I didn't have to let do you have it?
Oh, wait, you got remove the
We have extra.
They're like seconds.
Okay,
That people had to show their ID
and then,
class.
like, that's the first part. And the second part is not right. And also, yeah. Wait, but alright,
Oh yeah.
No, I can't get any. No, I've gone beyond
It might be a lead in disguise. There might not actually be.
I thought it was, but I guess not.
Yeah, that's also a problem.
I still fine. So I can bring up, but this, I haven't gotten this. And I use LinkedIn messages a lot, and it's not
Everything's safe. I remember the final.
I'm not. I'm not spectrum. It's not. No, I am. I'm sure everybody.
Hello everyone. I hope you're all enjoying your food. Yeah, so we're going to be starting the next part of this presentation very soon. So yeah, I hope you enjoy. We're going to be learning more about the architecture.
Okay, I prefer not to use a microphone. Is that okay with everyone? Cool. So hello and thank you for coming. My name is Elad Lab. I'm the lead architect for QNX. I also happen to be a Waterloo alumnus. I've been with QNX for 13 years now. Most of the time spent on the QNX kernel team. And I've spent the last 5 years designing the kernel from scratch. Mostly to address scalability concerns on many cores. Now I understand, or at least that's what the organizer told me, that there's a mixed crowd of younger and older students. So this presentation will start with some basic stuff, and as time permits and people are interested, we can go more into the reading. So, what's an operating system? In the most general form, it is a hardware abstraction layer. It allows me, as a user of the computer, not to care about how the hardware works. I can, as a user, I can open a file. As a developer, I can read a file, and I don't care how the disk drive works. That did not used to be the case. If I want to send some data over the internet, I don't have to know how the network interface works. Most operating systems also provide a multi-program environment. That means that you can have multiple programs running concurrently, and the operating systems ensures that each one sees as though it has its own machine, that it can monopolize, and it's going to interleave the execution and make it all seem as like it's working flawlessly. The third thing is a multi-user environment. That's one of the original use cases for an operating system. You had a big machine, and students would come and log in at all times of the day, and each of them would get their own environment. That's not much of a case anymore, but most operating systems, at least the non-trivial ones, still support multiple users. Now, do you need an operating system in order to run a computer? The answer is no, absolutely not. You can write the software that runs everything yourself without an operating system. Many microcontrollers still work that way. However, as soon as your hardware becomes more complicated, as soon as your software becomes more complicated, an operating system becomes essential. What is the QNX operating system? Well, it's a Unix-like complete operating system. Many, especially RTOS as others say, we're POSIX. But what they mean is very small subset. Yeah, we have the pthread API. QNX is a complete operating system, Unix-like. In theory and in practice, anything that you can run on Linux, anything that you can run on Mac OS, you can run on QNX. I would advise you to use QNX in a server or desktop environment. That's not what it's optimized for, but it can do those things. It's optimized for the embedded real-time use case. It's based on a microkernel. Until recently, I believe, to the best of my knowledge, it's the only commercial complete operating system based on a microkernel. Huawei has recently advertised that the new operating system is also microkernel based. It's a low latency real-time scheduling operating system, but unlike many of the RTOSes that you hear about and may have encountered, it requires modern hardware. So QNX, as of version 8, the current version, 64-bit only. It runs on x86 and AR64, RISC-V maybe when they actually have hardware. It supports up to 64 cores and up to 16 terabytes of RAM. So when you're looking at something like the Raspberry Pi Pico or Arduino with a few hundred Ks, QNX is not for you. QNX is for the cases where you want real time, you want the safety, but you need to run on a big system with a lot of memory and a lot of compute power, and have this mixed environment of more critical and less critical pieces of software. So now let's talk about kernels. What is a kernel? The answer really depends on the system that provides the kernel. There isn't a one definition that would satisfy everything, but in most operating systems, the kernel is always resident in memory. It's the only part that's always resident, it's always there. It runs in a privilege mode, which means it can control the execution of everything else within that machine. Now I'm saying machine here carefully because for the last 20 years or so, virtual machines have been very popular in various scenarios. It started just in the big rack server space, but it's getting everywhere. When you run in a VM, the kernel only controls the execution within the virtual machine. It has no control over what executes outside of the virtual machine. And this is why I believe, at least, that if you put a real-time operating system in a virtual machine, you're giving up some of your determinism, you're giving up some of the control. So when we talk about our hypervisor, we typically mean we're going to run QNX as is, but QNX is also going to serve as a hypervisor for Android or some other operating system that runs non-critical stuff. But the real-time scheduling still applies to those critical components within this combined system. When we're looking at kernels, typically there's a very broad classification of a monolithic kernel versus a microkernel. In a monolithic kernel case, almost all of the OS services are inside the kernel, to the point that the kernel is almost synonymous with the operating system. When you say Linux, a lot of people interchangeably use it for the kernel and for the complete operating system. And some people, especially on the GNU side, always hate that. How do application processes interact with the operating system? They do it by kernel calls. Because almost all operating system services are in the kernel, you need to make a kernel call to get to those services. Now there's almost no separation within the kernel between the various services. In a microkernel environment, on the other hand, there's just a few services within the kernel that run in privileged mode. And many components that you would consider a part of the operating system run as normal user mode processes. So it can be your file system, your network stack, USB, graphics. Each of those is a separate user mode process, and typically it does not have any more privileges than any other process. How do application processes talk to the operating system? They do it in two ways. One, they still talk to the kernel, they still talk to the microkernel via kernel calls, but they also talk to other services using what's called inter-process communication, or IPC. And IPC is crucial for a microkernel-based operating system. So if I want to read a file, then I need to talk to the file system server. And that is done through IPC. IPC itself is a kernel call. And this is what this blue line is trying to represent. We have an application process going through the kernel to do the IPC call, and the file system service can then handle that. So what are your design choices when you want to pick up either a monolithic kernel or a microkernel? Monolithic kernels are typically faster. For the exact reason that the way I described it, if you want to get at a service, all you need to do is a kernel call. And the service is already there, fewer context switches, fewer components involved, and you have what you need. There's better integration within services, between services within the kernel. So because there's no separation, that means there are also no barriers. So different components can talk to each other without any barriers. This comes in handy when you want to implement something that is a hybrid feature between multiple components or multiple components. A good example for that is the file system cache, where it involves both the memory subsystem and the file system. And that's a lot easier to do in a monolithic kernel than it is in a microkernel. But microkernels are complicated. The beasts. And finding or analyzing the monolithic kernel for all possible bugs is a very hard job. And the implication of those bugs, if they exist, is much more severe. Because there's no separation, I can have some poorly written driver that's going to access some piece of memory, and it's going to write over something critical in the schedule. And in contrast with the microkernel architecture, because it's much smaller, it's much easier to analyze, much easier to find bugs. There's even a microkernel out there, SCL4, which has a formal proof of its correctness, which is something that cannot be done on a monolithic kernel. Now that proof comes with lots of caveats, but the fact that they did something is already impressive. the microkernel operating system is robust. Because those services run separately in isolation, services can fail and the system as a whole can still continue running. Again, there are caveats, and it's important that people are aware of those caveats, because not every service is the same. And it also depends on what do your critical applications do. So if I have my critical application is some engine control process that, because it's safety, it runs once, it stays in memory, and once it's running, it only touches the hardware and the sensor, then the file system can fail as far as I'm concerned. It's not using any files, and we can restart it. But if my critical stuff is using a service that's failing, that's a much harder conversation. It's not impossible to do, it's not impossible to recover from this shared state, but it is hard, and most systems don't do that. Maybe most integrated systems don't. A microkernel is definitely more secure. There's much less code running for much less time in privilege mode. If you heard of attacks like Spectre and Meltdown, when they can get into the kernel and get passwords from your network cache and stuff like that, well, guess what? We have no passwords in our microkernel. So even if you get to it, you don't see anything that's important, because that's isolated in a separate process that's part of the network stack. And finally, it's much easier to develop OS services because you don't need to be a kernel developer. You don't need any special requirements beyond those of I need to know how to program in a programming language, because in order to write a file system, all you do is write a pretty normal piece of software. And you can debug it as pretty normal piece of software, not with kernel debugging facilities and everything that entails. So about the QNX kernel. The QNX kernel comprises, it's a microkernel, it comprises 3 different execution environments. We have Muon. Muon does almost nothing. It does thread scheduling and handles exceptions. We'll talk a little bit more about thread scheduling if people are interested later. Then we have Neutrino. Neutrino is what you would expect the kernel to be. This is what handles the kernel calls when you want to create a new thread, when you want to send a message via IPC, when you want to lock a mutex or start a timer. These are kernel calls. They execute in this Neutrino, which is actually a thread changing what we call its persona from user to kernel, but it still runs as a thread. Even though it's executing kernel code, it's running as a thread. And then we have a few services that run in normal thread mode, and that's the process manager, the memory manager, and the path manager, but they're bundled together in one process, which is the kernel. So is the QNX kernel a true microkernel? The answer is yes, absolutely. It only has the components that are needed to run in privileged mode and nothing else. File system executes as a separate user process. Many file systems. Network stacks execute as a separate user process. Graphics, the GPU driver, the USB driver, each of those is a separate user mode process. That said, people who are microkernel purists may object, or the L4 crowd may object, saying, oh, why do you have the memory manager in your microkernel? And the reason is it's a pragmatic compromise. Putting the memory manager outside the kernel, because the kernel itself needs memory, would have complicated the design considerably. And if you think about the rationale for having a microkernel, the memory manager doesn't apply as something that can fail. If your memory manager fails, your system is toast. And it cannot be isolated, because by design and by definition, a memory manager needs access to all page tables. So it can do whatever it wants. So this is why putting it outside does not buy you anything from the philosophy, from the point of view of the philosophy of the microkernel design. And putting it aside would have complicated things a lot. So even though I said there's microkernels and monolithic kernels, in reality there's the spectrum, and yeah, you can see this is where things fall, and some other systems. macOS actually started as this kind of hybrid between a microkernel, and then they added some other stuff that runs with a microkernel, and it grew a little bit. So yeah, but QNX is a microkernel. I want to stop here. This is the end of the more general thing. I have a few more slides, not too many, that go really into details. Are people interested?
Yes.
Very good. Any questions before that? Yeah.
How did you come up with these names? What do you want to neutrino?
So neutrino is before me. I guess that the people, neutrino was 96, and I guess they were physics buffs, and they just wanted it. And when I started writing and separating the scheduling into a new component, I was in the shower going through all the subatomic particles I've heard of, and that sounded good. Then, of course, the physics buffs told me that muons are much heavier than neutrinos, so it doesn't work. But that's what happens when you give a software developer a physics assignment. Okay, so let's talk about scheduling. Scheduling is one of the most important things of any operating system kernel. No matter how micro you go, you still need to do thread scheduling. So, what's a thread? A thread is a sequential stream of execution. There are many definitions out there that are wrong. One of that you may read is lightweight process. That's wrong, forget about it. It's a sequential stream of execution. You have instructions and they execute one after the other, or jumps and so, and it has a stack, and it thinks it owns the CPU. It just goes running. And what the scheduler does is it takes multiple threads and interleaves them. It says, now you run, now you run, now you run, now you run. So essentially it's an arbiter of the CPU. So the thread then executes until it is preempted. That means the scheduler decided that something else needs to run, or that it blocks. It makes a kernel call that needs to block and cannot proceed until something happens. In QNX, the way the scheduler decides which thread to run next depends on something that's called the scheduling policy. And different operating systems provide different scheduling policies. Muon itself, which does almost just scheduling, has a very simple, very deterministic schedule. Because the whole point of Muon was, I need to run the most eligible thread as soon as possible. Talking about low latency real time. Now, there's a complication. The complication is that we run on these big machines up to 64 cores, and some threads, the people who write the software say, you know what, this thread can only run on this processor, or on this subset of processors. So you don't have complete freedom to decide as the operating system. The way we address this is something called scheduling clusters. Now, the thought behind those clusters is, yes, threads can be bound to these subsets of processors, but there's only a few subsets that are interesting. One subset is all the processors in the system. Another interesting subset is just one processor. So a cluster for processor 1, a cluster for processor 2, a cluster for processor 3. This is a use case when you're dealing with hardware. You want a thread to run only on the CPU that has access to certain registers, to certain networks. Then you can have a subset of processors that are of interest to you as a system designer. For example, many modern systems on phones and elsewhere have big cores and little cores, or efficiency cores and performance cores. So a cluster of interest would be all the big cores, and a cluster of interest would be all the efficient cores. But there aren't too many of them. So if we go back to how do I make a scheduling decision that's efficient and fast, the observation is that let's say that we're doing the scheduling decision on processor 2. Processor 2, even if I have a lot of clusters in the system, processor 2 is only a member of this everything cluster, the cluster that contains just itself, and maybe it's a member of the big cluster along with cores 0, 1, 2, and 3. So we only have 3 clusters of interest for processor 2. When we come to make the scheduling decision, we look at all of the threads that are ready across all these clusters. Now that can be a lot of threads, but because we're doing highest priority, longest waiting first, really the only threads that are eligible to run at this point are T1 and T8. Does that make sense? So we're not looking at lower priority, we're not looking at anything that's later on the list, we're just looking at the head. Often there's going to be just one candidate and then we can make a fast scheduling decision. You go, you're the highest priority, no one else is at priority 254, you go. But if we have a tie, then we compare the timestamps between T1 and T8. Oh, T1 has been waiting longer, it goes. So it's still an O1. For those familiar with algorithm analysis, it's still an O1 scheduling decision because the maximum number of threads I have to consider is 3. So we took a big problem. We had dozens of ready threads. We actually support, again, we're talking big system. We support up to 4,000 processors with 32,000 threads each. That's, I think, 128 million threads. We took this big problem and we shrunk it down to, okay, you have 3 threads at most to consider when you're coming to choose a thread. Questions about that? Okay, so let's talk a little bit about a kernel call. A kernel call is how a thread requests service from the kernel. And I mentioned before that in QNX, every thread has 2 personas. We started with calling them personae, and then people started conjugating Latin and it didn't go anywhere, so we're sticking with personas. So it has a user persona and a kernel persona. So we have a thread, we start with T1, it's running in its user persona, it's executing regular code, all of a sudden it needs a kernel service. It wants to know if this semaphore has a value greater than 0, and if it's not, it wants to wait until it gets posted. So it's going to execute a special instruction that traps, and it will trap into muon. Muon immediately changes its persona, does some register magic, says now you're privileged, now you're a kernel persona thread, go run in neutrino context. And this is where the actual kernel code is going to be. Find the semaphore, check what its value is. Oh, it actually cannot run right now, so let's block. And when we block, we need to pick another thread and we pick T2. So T2 starts running, it runs, it continues something that it did before, and all of a sudden we got an interrupt. And the interrupt is serviced by T3, which has higher priority. So we're preempting T2 and we're allowing T3 to run until it blocks, allowing T2 to continue. At some point in time, T2 is going to post to that semaphore that T1 was waiting on. So it's going to make a kernel call into muon, into its kernel persona, make T1 ready. T1 will now complete its kernel call, go back to muon to change it to its user persona, and then continue running kernel user mode code. Now this may sound very complicated. It is complicated, and there's definitely some overhead. So why do it this way? The reason is that outside this tiny, I didn't bother to scale. Outside these tiny periods of time, everything is preemptible, including kernel context. So while T1 is running in kernel persona doing the kernel call, it can be preempted at any point by a higher priority thread. So this is how we ensure low latency. Anytime there's any event, it doesn't matter if you're running user code, it doesn't matter if you're running kernel code, the system is always able to handle interrupts. Okay, so a bit about our IPC. As we talked about, IPC inter-process communication is how you get to most services in a microkernel-based operating system. Now, in QNX, the main form of IPC is called synchronous messages, and it's based on a client-server model. What that means is that we have a client thread that is requesting a server thread to do something on its behalf. So it's going to pass a message to that server thread, and then it's going to block. It's going to wait for the server thread to receive the message, and then eventually the server thread replies, at which point the client thread can continue. This is synchronous message passing as opposed to asynchronous, where the thread will just dump a message in a buffer, continue running, and at some later point in time get a notification, hey, your reply is ready. The big advantage of synchronous message passing is that there's no resource allocation as part of IPC. We queue the thread, we don't queue the message. We don't need to allocate anything. We're not concerned about a queue filling up because the thread is stuck there and it's waiting for the reply. And that also means we have an unlimited message size as opposed to most message passing systems where you can have, some of them are as small as 64 bytes or maybe a few kilobytes. We support per message transaction up to 256 petabytes. I don't think there's enough memory in the universe right now to actually do that, but if you can buy, then sure, we can do that. And many of our system calls, what you would call a system call, not a kernel call, a request for a service from the system, are actually implemented as synchronous message passing. So calls like read or write or fork to create a new process or POSIX to create a new process or map or get the parent PID, all of those are message passes. We also support asynchronous messaging. Main reason, people are used to it. And customers are just nagging us, why can't I do that? Even though it has its disadvantages, you have a limited buffer and you can overrun the buffer or you can exhaust your mode, but we do that and we support in the kernel POSIX message queues. Pipes currently run using an external server. We're bringing them into the kernel, and there's Unix domain sockets that some people love very much, even though it's pure overhead. And of course, you can also do shared memory. So finally, I want to talk a little bit about interrupts. So an interrupt is an asynchronous notification from the hardware that something happened, and you need to notice and take some action. So that can be a new packet arrived on the network interface. It can be a timer has fired. It can be a disk transaction is finished. All of those come in as interrupts. What happens when an interrupt comes in is that the processor, this all happens in hardware, it goes and it jumps to some known location and starts running what's called a handler. And in many operating systems, different drivers associate handlers, interrupt service routines with interrupts, and you jump to that and the driver will execute its code in privileged mode. Not in QNX. In QNX, there's really only one interrupt service routine in Muon, and all it does is decide what interrupt it was. Has anyone registered, any thread registered for that interrupt? And if so, it makes that thread ready. And that thread is going to be scheduled normally, based on priorities and how long it's been waiting. And this is where our interrupt handling happens. We call them interrupt service threads. They're completely normal threads, they're not privileged in any way, and they're scheduled normally. And why does that matter? It's because usually when you design a system, people take interrupts to be, oh, this is the highest priority thing for me to ever handle. But if you look at a complex system, I may be running a complex system with some critical components that's currently doing some very critical computing, and all of a sudden this the file system, the disk write comes in and says, oh, I've just completed writing a log. I don't want to interrupt this critical computation and go service the disk. As a system designer, I can say, you know what, my disk IST is only at priority 30. And my calculation that's critical for the correct operation of the system is at priority 100. So it is going to be scheduled even on, in preference to the interrupt. That's pretty much the end for me. I have a blog. If you want to go check it out, you can find the Raspberry Pi book there, a series on memory management, some more information on interrupt handling, and how you can use QNX on your treadmill, which I've been running on for the last 2 years, or even build a QNX desktop, even though it's not supposed to be a desktop operating system. Questions? Well, yeah.
Is the code for the QNX text open source?
Yes.
I would like to look at it.
What kind of systems does it run where it needs like 60 terabytes of RAM?
Currently, the highest I've seen is an Amazon machine with 512 gigabytes. So the fact that, and 64 cores, and then I thought that was really cool. Your average QNX system is still between 2 and 16 cores, but it's changing, and we had to be prepared.
So it's like more like future.
Yeah, yeah. So you definitely have gigs of RAM, and I don't even know anymore what's the minimum we can support. At one point, a couple of years ago, I was able to boot on an 8 megabyte QEMU because you can't get 8 megabytes for at least not for a 64-bit system. We had a customer not too long ago that built a system with 256 megabytes of RAM, and I didn't know where they got the chips. I thought maybe in a dumpster. You can't get, you can get microcontrollers with very little RAM, but when you're talking about the systems we run in, finding DIMMs that are less than 2 gigs, I don't know what you do.
I assume they don't run in back.
So, no, not everyone is running back.
Because like you don't have enough memory to run.
Oh, yes, that is a problem.
I'm going to steal the opportunity to ask the thread priorities, process priorities are obviously very important in terms of timing and whatever else. So, from a customer's perspective, how do they decide where to slot in which process?
So, first it's thread, not process, because due to legacy, very old legacy, some people still associate priorities with processes, and that we mostly just don't support it. So the priority goes on the thread. That means that within the process you can have threads of different priorities. How they decide is an excellent question. The reason you may ask, why is it that why on earth do we have 256 priority levels? Come on, it makes no sense. The reason it came is from something that's called rate monotonic analysis. And many years ago, this was the textbook way of how do you decide who gets what. The problem is that those were much simpler systems, especially with SMP. I don't know how you do rate monotonic analysis. So it is a very hard job, and a lot of people get it wrong and start playing with it. But most of the time, a lot of the software just ends up running it in a different priority level, which for us is 10 by default. And then you have a few things that run a little bit higher, and you try and keep the higher priority levels really to the things you are absolutely convinced are going to be critical. We even allow you to put a thread at a higher priority than the system's own timer service. just to get to this really low latency. And with that, on a system, on a complete system with 16 cores and 32 gigs of RAM, I measured, and doing crazy stuff all the time, I measured 20 microsecond latency for interrupt, which is crazy low for this kind of system. Usually you're talking about in milliseconds. But this is how we achieve it, but it is not easy to decide what's your priority and what you're willing to accept. And one of the things to remember, we keep saying, so autos, deterministic, real time. The hardware is not deterministic. Modern hardware is not deterministic. Modern hardware has caches. Modern hardware has store buffers. Modern hardware has all kinds of crazy things that go and steal the CPU from you. We had a system not too long ago from a very, very major hardware vendor. I won't name them. But every once in a while, the CPU went away for a while to optimize the instruction stream. I don't know how you deal with that and still maintain real time. Then there are the people who put the real-time operating system on top of a hypervisor, and the hypervisor decides to switch out the entire operating system. So again, I don't know how to deal with that. If you are ever the designers of complete systems, don't do that. But that's the world.
Do you ever struggle with like low priority processes, like not getting like time because you have to preempt the priority scheduling? So like, will they ever not get to run because you're continually getting interrupted?
Absolutely, absolutely. And so I don't have to do anything about that. We gave you the scheduler, we told you how it works. And the assumption is that if you, this is not a typical scenario, I put those 254 just for illustration, this is not a typical scenario. If you ever put a thread this high, your expectation, the expectation from you, is that it's very bursty. It's typically an interrupt-driven thread. It does very little and then goes back to block. If you don't do that, if you allow it to run and calculate high, your system stops. There's nothing you can do about it. So on top of that, we give you some ways of detecting that it's running for too long. There's also a division to privileged and non-privileged priority levels. So as a designer, you say, you know what, my cutoff is at priority 16 or 64 or whatever. As I said, we give you way too many priority levels to play with. Nobody running normal software can put themselves above the non-privileged priority. You need to get, as a designer, you can assign privileges or abilities. And that's one way to control what's going on. And the other way is to just put a watchdog thread even higher and say, oh no, my system is just not getting, I know that my thread here hasn't run for a long time. That means that something's starting.
Yeah, so my question is that you mentioned that the microkernel, one advantage of it is that the modular systems are easy to prove that they are secure. So are you doing the same for the QNX, and how do you prove it's secure and bugfree?
So we talked about kind of sizes of microkernels.
Mm-hmm.
The QNX microkernel is not as small. It still does a lot of stuff that L4 doesn't. So we support a lot of POSIX construct like semaphores and mutexes and barriers and all kinds of timers and stuff like that. L4 doesn't do any of that. So we thought we would go this way, we didn't. The other thing I mentioned before, that SCL4 had a proof but with caveats. The thing they left out because they couldn't prove was SMP support for multiple processors. 99% of our bugs are the result of multiprocessors and the way they interact, right? So you can have a proof on a uniprocessor, it won't do us any good.
Yeah, so because I heard that some languages, are provable by design. So maybe, I think in the future, maybe there's a domain-specific language you could utilize to prove your system.
So for domain-specific languages, I don't know if you can write a kernel. You can write, what you can do, and we did that a few times, is you write the same algorithm in a different domain-specific language and say, oh, I've proved that, therefore the code I wrote in C is good. It doesn't work. It gives you some level of confidence that at least your design is sane. It gives you very little confidence that your implementation is correct. There's other things that are coming in are languages that are better at managing resources and stuff. Rust is the prime example, and people have started writing kernels in Rust. I've started looking at it. So far, I'm not looking at it to replace the kernel. I'm looking at it to do things like file system and networks, like things that run in their own in user mode processes. And I think that's where you get the big benefit of something like Rust for us.
Right.
Because I think that if you write the microkernel in Rust, it would be just, I don't know how familiar you are with Rust, but it would be unsafe kernel, close bracket. It won't give you much.
That's like
Yeah, how do I install QNX on the Raspberry Pi 5?
There is a BSP. Was it officially released?
I'm sorry.
It exists. I don't know if it has been released officially yet.
I think it's like you need to get a license, and like in the software center you can just grab the image and just flash it.
Yes, but I don't know if we've actually released the RPi 5.
Oh, it's only for 4 right now.
Yeah, no, for no problem. But RPi 5
Not yet.
We have it, and then we demoed it, but I don't think we've released it publicly yet.
Here's the question. Go ahead.
How does that synchronous mesh being worked on like a low level? Because like I looked at trying to get typical cross communication working. I've only seen it like with like shared memory and through like asynchronous. I haven't seen synchronous yet. So
Can I write this someone? So, for message passing, we have the new friend, QNX Microkernel. That's going to fail, and now you're going to think that you're going to fail. So we have a client thread, and we have a server. Now, each of those has its own address space that it runs in, and only it can access. When we do a message pass, what we want to do is transfer some data from here into this address space. So this will be the message buffer. Here there will be a receive buffer, and we want to copy from here to here. All right? And we can't have the server just have visibility into the client, because that completely destroys all of our promises for isolation. Right? If the server, people who write servers would love that. Just give me access to the client and don't worry about it. But no, that completely destroys all the major point of the microkernel design. So we need to copy from here to here. We need to do it through the kernel, which is the only privileged part of the system. So we're going to do it through a kernel call and all the details I've described, but essentially what we do is we make a kernel call. The kernel call says, here's a pointer to my buffer. And this kernel call, this is the message send kernel call. There's another message kernel call, message receive, that tells the kernel, this is my buffer. So now we need to copy from here to here. Now it's tricky, because we cannot assume that whoever wrote the software gave us legit buffers. We cannot assume they're not trying to trick us, or they don't have bugs. So what we do depends on the size of the message. There's a short message up to 1400 bytes, and there's a long message. For the short message, we accept double copy. We copy from this buffer to another buffer in the kernel with And if that faults, we just say, forget it. We give you an error code. Then, when we go to the receive side, we copy from here to here. When part of this kernel code that does the copy also makes this client blocked. And that's the synchronous part. This guy gets a receive, it becomes ready, it continues running, it does whatever it needs to do. When it's done, it's going to make another kernel code with another buffer. This is the reply. The reply will copy to another buffer here, that's the reply buffer, and will also make this thread ready. So it was blocked for the entire time the server worked on it. Now that poses other problems. The main problem is that the client completely trusts the server, because the server can go away and not return. In the past, we used to say, that's life. You know, you're running with a file system, you must trust the file system. People are not buying that argument anymore, and it gets very tricky. Because the client cannot just disconnect itself, because now it's tricking the server. So we live, one of the hardest parts I find as a modern software developer is that we don't trust the people who write the software for us. And that makes life very, very hard. If we could trust everyone, sure, there are bugs. But if we could trust that they're honest, things would be a lot easier. The fact that we can't is tricky. So this is the short message passing. When you're talking about, I said 256 petabytes, nobody's doing that, but you can get, when you read a file, you can ask for, give me the contents of 1 gigabyte. That's completely legit. And that's a message pass. The way it works is that we talked about the user persona and killer persona of each thread. While this thread is in its, both threads are in the kernel persona, the entire address space of the client is mapped into the address space of the server. Now, the server in user persona cannot see it, it's not privileged. But when it's running kernel code that we trust, it can see it, and now it copies directly, because this is no longer a copy. This is just a different view of the same data, and it copies the 1 gigabyte directly.
So you eliminate the double copy.
Yes. At the cost of fiddling with page tables, which is prohibitively expensive. I've seen when I tried recently to publish a paper on about what we did, and one of the pieces of feedback I go back, oh, you must be looking into zero copy, where you do more things like that, and or even you don't even do this 1 copy, you just map it. And I don't think that those people realize, they come from academia and they sometimes don't realize modern hardware, how expensive it is to do certain things. For example, manipulate page tables. Why? Because your really, really fast laptops work on the assumption that everything is linear and everything is just going to go for a long time without any disturbances. If you, I don't know how old are you, and if you remember the times when computers got faster and faster just by upping the clock rate, every 6 months you get a new model that was so much faster because of the increased clock rate. That's gone. That's been gone for more than a decade. The reason your M2 or M3 MacBook is faster is because of large of speculation and very large branch predictors. And those things don't like it when you do things they don't expect. What don't they expect? They don't expect kernel calls. It's crazy, but they don't. They don't expect interrupts to come. They don't expect that you will change page tables. So all those things are prohibitively expensive. And this is why we have this 1400 byte cutoff. It's kind of, this is where things, where it's worth our while to start going and fiddling with page tables instead of doing the double code. It's actually more, you can get a lot more than that, but that's just how it, at least until 4 kilobytes, you're easily better doing a double code.
Yeah, so in the workflow you described, so are you using the CPU to copy the messages from one buffer to another? And is there a possibility to use DMA, which is direct memory access?
Right. Typically the answer is no, and the reason is that because it's a POSIX operating system, I mentioned that many of our codes like read, write, they're all implemented using message passing. And POSIX says, you can give me any pointer you want. It doesn't have to be page aligned, it doesn't have to be cache friendly, it doesn't have to be resident or always in memory. Give me a pointer, I'll copy it for you, why not? That's something, again, that you see a lot of papers in academia saying, oh, if we could allocate our buffers in a certain way, certain things would be a lot faster. That's true. But 90% of the software out there will not work because they expect to take a void pointer. There's the most crazy thing, IP packets. IP packets, it's not only they're not page aligned, they're not even word aligned. You have a 14-byte header. So, and that's why, yeah, it's, now, the vast majority, I talked about how we can do such big messages. The vast majority are very short messages.
You guys are like changing the page tables, just like mapping office one to office two server. Does that pose like some security risk?
So this is why the way it's mapped, the page table lets you say that it's mapped in privilege mode. So only code running in privilege mode can access it. Even though it's, yes, this is part of your address space, if you try to access it, supposedly the server has another thread. And he tries to say, oh, you know what? I know that there's a message pass going on. Let me try and sniff what's going on here. It's going to fault.
So one thing I'm getting confused about, like, does this memory mapping only, like the shifting of the page table only happen for like short messages or?
No,
like,
only for long messages.
Only for long messages. So for short messages, you can just double copy.
We double copy.
Okay, that makes sense.
Great. Thank you very much.
Before we all run out of the room, just wanted to suggest grabbing one of the cards from the table. Sorry, I didn't introduce myself. I'm John from QNX, I do developer relations. The cards on the table have a QR code that you can scan. Brings you right to where you need to go to get a free license to use QNX. So you can get started using it with a Raspberry Pi, or you can get started using it in VM if you want. And while you might not be able to go in and tinker with the kernel code necessarily, there's lots of things you can do today, like developing existing drivers or resource managers, or porting things from Linux to start building up your experience with Raspberry. So check it out if you want. There's also contact information there about our socials, where a bunch of the developers secretly monitor it under pseudonyms or known plumes. So you can also ask some questions there if you have easy questions or technical questions, and some of us will help to respond to those. That's all I got.
I'd also like to say some words on behalf of the Computer Science Club. So we at the Computer Science Club are very proud to hold this talk today, and we'd like to extend a lot of thanks to our speakers, to Matthew, to Elad, and all of the QNX team for coming here, for taking a tour of our lab, and for giving this talk to our club. In addition, we'd also like to extend a very big thank you to another one of our guests, to Leo Shan. So, as some of you may know, Leo is a University of Waterloo alumni, and he was also an advisor to the Computer Science Club. And with his help, we were able to get this talk. Without him, we would not have been able to coordinate any of this. So we'd like to extend very big thanks to everything he's done for us today. So as part of the career and community pillars of CSC, connecting our student members with people in the industry is something that's very important to us. Connecting with industry partners and alumni has always been a core part of our program. Industry insights and network opportunities give our members a unique view into the real commercial environment, something that's not very easily obtainable through just school, through just lectures alone. So with events like this, we strive to bring students more interesting topics and opportunities for growth and to learn more about the industry. So before we end this event today, we'd like to offer some gifts for Matthew, Elad, and Leo. So if you could come on, we have some things for you. So look at that. Thanks all. Awesome. Thank you so much. Great talk. I hope you enjoyed and for everyone who came here from QNX, we have some we have some other gifts for the people who didn't talk, because we still appreciate you coming here and spending your time with us. We have your keychains.
It's a